That spark of innovation, it's just waiting for the perfect combination of tools and talent to bring it to life. Welcome to Pitch, Build, Scale. I'm your host, Chris Fanchi, a recovering startup founder, veteran SaaS marketer, turned dev tech enthusiast and growth specialist. Each episode, we connect with the builders, the visionaries, and the problem solvers who are redefining what's possible with today's technology and pioneering the websites, apps, and software products of tomorrow. These are the conversations that transform how we build, how we sell, and how we scale technology businesses in a world where the tech evolves by the minute. Ready to stay ahead of the curve? This is Pitch, Build, Scale. Hello and welcome. Today we have a very exciting guest. For those of you just joining the podcast, we are Big North Marketing and specialize in helping dev shops and SaaS companies scale their revenue. If you want to learn how to take your SaaS or dev business to the next level, make sure to stick around. And if you're interested in a free growth consultation, just drop us the word growth in the DMs. We're really excited to have today's guest, Ira Baxter, CEO of Semantic Designs. Ira has been building systems since before Unix, spent decades in OS design and compiler tech, and now leads one of the most advanced software transformation companies in the world. His company, Semantic Designs, helps giants like Dow Chemical, NASA, and Northrop Grumman modernize massive legacy systems in languages most devs have never even heard of. From migrating COBOL systems with millions of lines of code to automating the analysis of software for aerospace and industrial automation, Ira's work is as deep as it is impactful. Ira, welcome to the show.
Thanks for having me.
So to get us started, Ira, you've been building software since before Unix. Can you walk us through that early experience and how that shaped your view of modern software development?
Well, yeah, okay. So I was lucky enough to have a father who got a degree in physics from MIT. And I grew up with a bookshelf full of books that he got from MIT, including books by sort of the computer science greats that came out of MIT. And these were really interesting books to read, because they had sort of people trying to do interesting things, like trying to build to solve mechanical mazes, okay? And I was probably about 8, okay, when I read this sort of stuff, and I thought, geez, that's really cool. The other thing that happened to me is a sort of really funny story about going into science. My father built crazy electronic stuff when I was a kid. I came home one day to find him in the kitchen, sitting at the kitchen table with an oscilloscope. That's the thing you see in monster movies with a sine wave pattern on it, right? Okay, and his circuit, which he built in three-dimensional stuff by soldering things together, a bunch of parts, and his flash strobe in the middle went off about every 10 seconds. Okay, well, I grew up in the 50s when monster movies were like the thing, all those black and white terrible B movies, and there were all these mad scientists in there. And I walked into the garage, I walked into the kitchen, I looked at my dad, I said, my dad's a mad scientist. I can be a mad scientist. Okay, and I think that was the real shape of my career. It's like, go do crazy stuff. Okay, because it's interesting, okay, and you can have a good time doing it. So that's kind of the sort of first thing. And modern software has got the same problem. It's crazy stuff, okay? It's great big giant systems, all sorts of complicated interactions, and you have to think about it carefully and understand it, put them together. The other thing I learned was lessons about editing, okay? I was initially interested in hardware because my dad did, so I built a bunch of hardware relay circuits, things like that. And to wire those things up, you had to use a soldering iron and wires and lots of patience and designs, and do a whole bunch of work to put them together. If you made a mistake, then you had to go back and cut a wire and unsolder things and resolder, and it took you hours. I learned to program in Fortran in high school through an advanced class. Our teacher took us over to local junior college and said, we're going to learn Fortran. So we wrote some programs, okay, and we wrote programs on punch cards for our IBM 1620. One of the lessons was if you made a mistake with a punch card, okay, you could A, make a new punch card, and B, if you made a mistake on the punch card, there was a thing called a rub out key. And the lesson was that editing software was way easier than editing hardware, okay? And that made me interested in software because it was easier to edit. Right? We now have large systems that are built by people. Everybody has a screen editor, and they have a delete key, and they use it. So we all think it's online editing to hack at things. And it is. It's useful to make changes fast like that and have fast cycle times for prototyping and trying things out. So I guess the other thing was sort of like, what's the relationship between hardware and software? So I worked with a lot of hardware circuits. As I was a kid, I did lots of digital logic, okay, using earlier versions of integrated circuits. Okay, and you end up building wiring diagrams and wire these things together to make them all work. Okay, one of deepest insights I think I ever got was that a circuit diagram, okay, an electronic thing, and a computer program were actually sort of the same kind of thing. When I look at code these days, I don't look at text. I do look at text, but I try to think about how information flows in that. There's actually a large set of activity in the compiler community that talks about converting source code text into what are called data flow graphs. And then the compiler then operates in the data flow graph by pattern matching against that thing. Those data flow graphs and the logic circuits look exactly the same when you step back and think about them. So I don't think about hardware and software as being different anymore. One's harder to edit.
I'm sure things are a little bit easier to debug now than they were back when you had the punch cards, right?
Well, yes and no. Okay, I mean, when you had a 1,000-line program, you were pretty sure the problem was in the 1,000-line program. Okay, when you got 10 million lines and something goes wrong, you're pretty sure you don't know where the problem is.
Yeah.
It's a much harder problem locating things. In fact, testing's really difficult. The operating system business was kind of interesting. I ended up working. I went as an undergraduate to UC Irvine, and I was bored. I went to there was a wall that had posted jobs. This is 1969. And there was a job up there that said key puncher. And I was looking for anything because I was doing $1 an hour working for a drugstore at the time. It said $2 an hour. Cool. So I went and found this place. They said, "Can you type?" And the answer is sort of with a rub out key. Had a little bit of experience. So these people were a place called Educational Data Systems, and they wanted to sell computer systems to every school on the planet, which has been an idea that's been around since the 50s. People keep repeating it. Let's sell computer systems to schools, right? They wanted to do this in 1969. Okay, and the apparent thing to do was to build something called BASIC, Kemming and Kurtz. Okay, so Educational Data Systems, with the help of me and one manager, built this Kemming and Kurtz basic interpreter, ran a data General Nova, and they sold it to a local college. The local college thought this was great, but there was only one terminal and they had 30 students. So I said, "Can you make more somehow?" Okay, so during the summer, that was I guess the summer of 1970. My boss, the company was doing badly because it only sold one system. Okay, so my boss decided I'm going to go out and help the president sell. You do something. Okay, and what I want you to do is I want you to make a basic that multiplexes itself. Okay, and this is where the mad scientist part comes in. It says, why would you want to do that? Why wouldn't you want to make a time sharing system that runs basic? It's a simple inversion, but you get really different answers depending on how you do it. So I
Mm.
did that. Okay, when you boss first found out what he did, he yelled at me. He said, "Oh, maybe that's a good idea." So I think part of what's interesting is that when you build these systems, you want to be ambitious because if you build, you're only going to build one of them. It's going to take you a long time to live with it, and you don't want the lousy answer. You want the better answer.
Yeah. Yeah.
Now, from there, okay, the really interesting thing happened. So I designed an operating system there on the Data General Nova, and I worked on it for a couple of years for EDS. Okay, so it was like 6 to 8 months of designing the OS, and then there was like 2.5 years of enhancing it. Okay, well, EDS eventually went out of business, and I went on to doing something else. Okay, I started up a small company called Software Dynamics in 1970. Three, something like that. And I built another operating system. And that one took me a year to build. And then I spent the next 8 years busy trying to sell it into the marketplace against Bill Gates. I lost, okay? But it was an interesting experience. But the lesson was that when you built one of these things, you spent a modest amount of time building the new one, and then you spent a lot of time enhancing it. Okay, when I figured out that Bill Gates had won the war, I decided to go back to graduate school. Okay, and I thought what I should do was to understand why it was that I knew I knew something about how to build new things, but I didn't know what to do about enhancing and modifying old things. Where's the guidance? Where's the And I thought the people in the university might know the answer to this question. So I joined the master's program, okay, at UC Irvine, asked the software engineers there, so how do you modify old code? And they went, huh? They had no clue. And they mostly have no clue. But that's the problem. That's the real essence of these systems. You build a system, it takes you a certain amount of time to build it, and then you have to maintain it forever. And if you look at the reality of these large systems, that's exactly what happened. They built a system back in 1975 on a mainframe, okay, and it worked, and then they enhanced it for the next 30 years. Okay? And so their investment is in those enhancements and not in the original thing.
Right. Right. So you mentioned in our earlier call that maintenance is where the real cost of software lies. So why do you think that insight is still overlooked by so many companies today?
Well, it isn't. Okay. I mean, most of the companies that are out there that are doing work actually do maintenance work. Okay, if you look at every large corporation in America, okay, Ford, GM, whoever, okay, they make whatever they make. They're not software companies, okay, and they may have a software staff, but a large number of them hire what's called a system integrator. Okay, a system integrator is a large company that will code for food, right? And the system integrators say, yeah, well, yes, Mr. Ford, we'll help you build and maintain all of your software systems for the vast amount of money that flows to us over a permanent uh, engagement. We want to put somebody in your, at your site for $75 an hour and leave them there forever. And there's our revenue stream. But these companies do know about this. It's not clear that they have a real motivation to fix the cost. Okay. If suddenly maintenance got 1,000 times better, their cost revenue streams would go down. So their motivation's sort of less than you'd think, right? Now, I think part of it is they don't know what to do. Okay, that's fair. All right. And to be fair, I don't know what to do. Although I spent a PhD thesis on it, trying to figure out what to do. Right. One of the things I think is fundamentally wrong. Okay, and we have to cure this. And I don't have the machinery to do it, and nobody else does either. We need to capture the design information behind these things. If you ask somebody that's employed by a big system integrator or anybody else building a big software system, I need this change made. Okay, well, where is it in the code? So your first problem is finding it. We have no good weapons for finding things, okay, in a 10 million line system. Okay, and then your second problem is making some kind of change to it. You're changing a piece of code that you don't understand, okay, to do something that you think you understand, okay, without breaking the rest of the system. This is pretty hard to do, okay, and I think the reason it's so difficult is because there's no signpost left anywhere. People look at comments to kind of help guide them. Okay. Yeah, here's a comment. It says x equals x plus 1. Oh, that's what the statement said. Why did you write that comment? It wasn't helpful. Okay. Increments the age of the database. Well, that might be more useful. But comments are pretty vague. Okay. They're English. They don't carry well. There's not much in them. People don't put them in. I've seen big systems with like no comments at all. Okay. And you wonder how people keep this alive, and the answer is expensively. The real problem is there's no signpost left in the code to help you find anything, okay? That system had some kind of design when they put it together. These pieces fit together in this kind of way. We intend for this to do that. Okay, this module accomplishes this purpose. Okay, much of that information is lost. Okay, nobody bothered to type it in because the boss said, get this done. I don't have time to type in comments or signposts or extra information. So we need some way to capture all this design information. We need to capture the specification. What does it do? Right? You look at these big systems, ask people what it does, and the answer is, I don't know, actually. It just runs and does its thing. This is a fun problem with the Social Security Administration right now and all the Doge boys. It does something, and they can break it, and God knows what happens after that, right?
Right.
So you need to know what the specification is. What does it do? You need to understand what a high-level architecture is for the thing. Okay, how's it basically structured? You need to understand how the lower level code comes about from that high level structure and the specification. You need all that stuff tied together in some kind of mechanical way that a tool can help you navigate through it all. And my PhD thesis was basically about that. It said, here's a crazy scheme for doing this. Okay, and the good news, it was a crazy scheme, and it looked like it might actually have some theoretical promise, right? I finished that in 1990. Okay, that would have been a while ago.
Mhm.
Okay, and if you asked to characterize the rest of my career, it would have been looking for the pieces of the machinery to do that. And one of the major pieces is something called a transformation system. A
Mhm.
transformation system maps formal specifications to formal code.
Okay.
It's kind of like algebra for programs. If you take a look at regular algebra, you can say somebody says x plus 0, there's a specification. Well, a transformation on that is to remove the 0 because it doesn't matter for performance. So x plus 0 is your spec, and the implementation is x. X is simpler and faster to run than x plus 0. That's called compilation. Now, the differences between, sort of algebra and algebra for programs is with algebras, your formulas are small enough so you as a person can write them on a piece of paper. Okay, and when the formula gets to be, 4 lines long, you can stop writing them accurately because you just can't transcribe them. You're not good enough. All right. When you have a 10 million line system, it's a 10 million line artifact that you're applying the transformation to. Okay. So the difference here between algebra and algebra on programs is simply the simple view is it's just a matter of scale. And then, of course, there's all the engineering that goes along with that. Yeah, okay, it's just a matter of scale. Now you have to make all that work. That core piece of machinery allows one, if you can use it, transform specifications to code. Specifications come in two flavors. One flavor is truly abstract, okay? Sort of Z, right? That means take Z and get it sorted somehow. That's a high-level spec. Okay, another kind of spec is a really low-level spec. That piece of Java code you're staring at, that's a specification for a computation. Okay, it's transformed by a box called the Java compiler. You don't ever look into it, so you don't think about how it works. But the point is, it's a spec. So if you take the transformational viewpoint and you think of specs as being arbitrary languages in which you can say things, and they can be at arbitrary levels of abstraction, okay, then you can transform high-level specs into low-level code. That's hard to do, okay? But you could transform low-level specs into low-level code. And that's the basis of the migration business, okay? Map these constructs in COBOL to those constructs in C#. So the idea was, when I started the company, was let me see if I can build this transformation engine thing and make it work for legacy stuff, old stuff, because there's a lot of it around. That was the lesson from the operating systems and the universities. Right? Let's see if I can make that work. And then if I've got that core transformation piece of machinery, I can think about the other parts that my thesis said, okay, which are design traceability, capture all the design information. I can think about doing that. Okay, well, the good news, I got the transformation engine. It was a lot harder to build than I thought. Okay, we've been at this for 25 years. The first 5 years, it literally didn't work at all. But we've been doing work since then with it. Okay, but I've been so busy that there's been no opportunity to go back and take into account the design information. If I were lucky enough, so somebody came along and handed me $1 billion and said, "Here, we'll take Semantic Designs, we'll go run it, go do what you want," I would go back and do that.
Yeah.
I don't think that's going to happen.
So let's dive a little bit more into semantic designs then. What are you guys doing right now? And how much has what your current mission is, how much has that been influenced by your past and your thesis back in the 90s?
Well, let's just start with this. The company wouldn't exist without the thesis. The thesis said you need a program transformation system to do this. Okay, so the company was founded around the idea of build that piece, then at least I have one of them. Okay, but let's say the literature is full of how to do that. Okay, and in the middle 60s, program transformation systems, things that change code automatically were considered to be AI.
Mm.
Okay, well, they exist now and people know how to do it. Nobody calls it AI except our competitors. They're doing program transformation, sort of, kind of. What kinds of things are we doing now? We recently focused on the COBOL space. We were doing more exotic things because it was easier to sell the weirdness that we were to people that had weird problems. Okay, so the Dow Chemical people came to us in 20,000 and 2008, 2010, and said, we want to convert 800 factories, okay, using this really weird programming language that we invented. We're a chemical company. We invented a programming language. What could possibly go wrong, right? So they had a really strange programming language and they wanted to move it over to modern controllers. Okay. And they came to us and we said, yes, we could do that. 2 years later, we did that and we gave them a tool to transform their legacy systems. And they're still applying it because 800 factories are not easy to change overnight. So that's been going on for 12 years, something like that. But that was the weird business. Okay. Namely, transform weird stuff because people that had weird problems, we were the only solution. We turned sort of to COBOL. Okay. I don't know. 2022, 2020. Yeah, probably 2020, 21. And the reason we turned there is because we kept seeing people talking about migrations that had been done that turned out to be just as okay. Now, this is sort of funny because we took a shot at doing COBOL transformations back in 2000. Okay, we actually built our first transformation tool for COBOL, and we couldn't sell it to save our lives. And the reason is largely the clients didn't seem. Some of us, they weren't really motivated enough. Yes, we want to do this, but no, we don't want to do it really badly. Part of it is motivated by what I would call fear. If you're a manager and you take on some strange project like this, okay, if this project succeeds, that's good, and you might get some credit for it and an attaboy. This project fails, your career ends. Okay, and so they're looking at us and going like, let me see, you're going to stick an egg beater in my code, and I'm supposed to expect that the answer is going to work. That's pretty scary for those guys.
Yeah.
So COBOL migrations happened, but they weren't very often, okay, and they were really hard to win. So back in the 2000s, we gave that up and went off and doing the strange language stuff because that's a place where we had leverage. 2020, we decided to come back to it because we heard that people were now doing COBOL migrations. Acceptance had gone up. It wasn't a strange thing as possible. There were some success stories, but there were lots of failures, and there were lots of people who got, yeah, I converted this thing, and then I got really strange code that I can't maintain. I've actually had, I've actually had a couple of requests for proposals from people that have gone through a migration with a bad tool, got
Mm.
unmaintainable code, and they said, "Can you come in and clean up our unmaintainable code?" It's like, why don't you just come in and translate your original code?
Yeah.
Instead of producing something bad and trying to fix it, let's just produce the right thing. So we started to do that, okay, and it's beginning to gain traction. All right, we did I guess, a system that we're just finishing now is not COBOL, but something called Natural. Natural is a mainframe language that's sort of a bad copy of COBOL.
Mm.
It's the right way to describe it, okay. But early days of the mainframe, people sold tools, okay, to developers and managers, okay, of all sorts, okay. So that particular system is 2.5 million lines of natural code, 1 million lines of VB not 100,000 lines of mainframe COBOL. And the problem was build translators for all three of those whose output is compatible in the sense the pieces integrate to give you the right answer.
Mm.
I'll say it's been a tough project, but we're there. We seem to have gotten through it. It's now going under test for delivery to the end client. So that's one complicated example. The next one we're doing, and we're just starting this one now, is 7 million lines of Fujitsu Net COBOL. Okay. It has another COBOL in it called AccuCOBOL. Okay. The client said, we don't want you to convert that. We think we can convert that part ourselves. And my response is, you're nickel, right? So that's fine. Okay. That's going to be one of the things that could cause grief in the project. Okay. Can you guys actually deliver? But if not, well, it's a different COBOL. Oh, you know what we do? We build COBOL translators. If they screw up, we can pick up the pieces and probably maintain it. But it's 7 million lines of code. We're bidding on a project. It's got 15 million lines. So what's happening is the systems are getting bigger, and the bigger the size is, in some sense, the more motivation these guys actually have to move. Okay. It's one thing to have 1 million lines of COBOL and hire 3 COBOL programmers to maintain it. You got 15 million lines. Now you got to have 50 programmers around. That's a big pool, and they're hard to find. Okay. And the problem with much of the COBOL programming population is they're close to retirement or they're dead.
Right. Right.
Okay. So people are beginning to figure out, like, if we don't do this, we're going to be in a really funny place in 2 years.
Yeah. Yeah. Would you say that's been the main motivating factor? The reason why these companies are willing to do it now when they weren't 20 years ago is that the population
No,
of
I think
engineers.
it's a wide variety of things. Okay, the collective driver. Okay, is enough to push them over the link. It's like, I'm not going to be able to find programmers. One of the really best reasons for modernizing a legacy system is to expose the data. Data runs the business, and if you can't get at the data except through this one application, then you're hamstrung about what you can do with it. Okay, and so quite often a very strong reason for motivation is to move the database from whatever legacy database ran on your mainframe or your mini computer. Here we've got a index file system application, okay, from Btrieve, and we use that to build that. And nobody can get at that because it's not a widely used API. We want this converted over to be, in a SQL database so that we can actually write SQL programs against that data that are outside the current application. So that's a really strong reason. Okay. Another reason has to do with the nature of the tools. Okay, the COBOL development tools have never been really great. Okay, now Broadcom is making a serious push, okay, into building serious development tools for COBOL. 25 years too late, in my opinion, but there they are, and so they're putting forward, what amounts to Eclipse interfaces, okay, with all the sorts of tools you'd expect to have. So they're bringing that thing up to speed. So there's starting to be finally a decent development environment. But you can argue that, Broadcom's just trying to put this together, okay, and they're going to have a lot of teething troubles getting that right. Or let's just translate this whole thing over to C sharp, okay, and then I get development environments that are 30 years old and have the muscle of Microsoft behind them, okay. And I think that's actually a pretty good reason.
Is there value in sticking with COBOL? Is there something that COBOL does well that other languages, more common, popular
Well,
languages don't do?
the answer is COBOL. COBOL is just a programming language. Okay, it's clumsy in its own ways, but they're all clumsy in their own ways. It has one serious defect, which has to do with data overlays. All the data is organized around bytes, and you can overlay data on top of each other. And that means analyzing the programs is hard. Okay, but if you have a running system, okay, and you think that you're not going to have a maintenance problem down the road, a serious maintenance problem, okay, then in fact staying in COBOL is not a bad idea. Okay, people have gotten 30 years out of them so far, right? they can probably get another 30 if they try. So it's really a case of what are you trying to achieve? If all you want is stability, if you've got a system which is running, especially if you think you're going to get a replacement system in several years, then there's no point converting it. One really classic example, okay, are the guys that show up and say, we're interested in moving to an ERP system. We have a custom application that we want to move to an ERP. And you can do that a couple different ways. The usual way is an ASCII where you go get an SI and you say, here, you figure out how to move all the actions and data from the old legacy system into the ERP by incremental process. SAP is famous for this. But those processes are extremely expensive and they take a long time and you're not sure they're going to succeed. So if you have an existing running COBOL system and you're absolutely sure at the end of 3 years your ERP system is up and running, then you shouldn't change it, okay? Let it do its thing until you can switch, okay? Beware of the fact that you might not be able to switch. We've actually done it. We actually did a migration for a client that said, I'm going to get, 3 to 5 years from now, I'm going to be on an ERP, but I don't know if I'm going to be successful. So we did an automated conversion for him as an insurance policy.
Mm.
And my guess is what's going to work, we did that one about a year ago. He's still thinking about how to do the ERP thing, okay? My guess is that he's going to discover that having a bird in the hand is better than thinking about an ERP in the bush.
Yeah.
Okay. So that's kind of a different insurance policy and it might just turn out to be the right answer for him in the long term.
Yeah. Interesting.
Okay.
So,
Now there's one more reason to remain in COBOL, and that's that you can't move fast enough to get out. Okay. There's arguably 400 billion lines of COBOL out there. There's maybe 100 companies that do modernization of the convert COBOL to something else. In all kinds of ways they do it. There's the offshore guys that do it by hand. There's us who do it with high automation. There's people that are in the middle. Okay, we're now seeing a new wave of folks that says, "Oh, we're going to use AI to convert it," and I'm trying to contain my laughter. But there's there's 100 of us companies, and we can each do 10 or 20 of these systems a year. Okay, I'm small. I can do 2 systems a year now. Next year, I'm lucky. I'll do 4. But assuming I can do 10 a year, and the other guy can do, that's 10,000 systems a year. That doesn't make a dent. So what's going to happen to everybody else if we're all, they're going to have to stick with it. They don't have a choice, right? So it's an interesting problem. They have to maintain it into the future.
so go into the AI thing a little bit more. Talk a little bit about what you guys do in terms of automation and how you compare that to our modern AI and why you think it's so laughable that someone might try to do what you're doing using our modern AI tools.
All right, so let's talk about what we do first of all. It used to be called AI, okay? So we build these things called program transformation systems. A program transformation system is something that takes a set of rules. Each rule is the form of, if you see a piece of code that looks like this, replace it by a piece of code that looks like that. That's it. That's the whole trick. Now, it's funny because that's the whole trick behind mathematics. It's why mathematics is successful. It's the substitution principle, right? Okay, and that explains why you can actually make it work. You can transform these things incrementally. Okay, and get across the boundary to convert the system. This idea of transforming programs automatically, okay, in the 1960s was funded by the Air Force, okay, as artificial intelligence. And people built some initial program transformation systems, and that's kind of where I learned how to do it, right? By watching these other guys do this sort of stuff. But ultimately, it turns out if you see this pattern, replace it by that pattern, okay? That doesn't actually seem on the face of it like something is actually intelligent. It's just pattern replacement. Yeah, it is. It's just pattern replacement. If you have one pattern replacement rule and you apply it, not much happens. You have 10 pattern transformation rules and you apply it, and some stuff happens. You have 10,000 transformation rules and you apply it to a 10 million line system. Amazing things happen because the code gets changed by all these different patterns that are doing different kinds of things. But that's not AI, in my opinion. It's massive application, okay, of the tool, right? The second point is that a lot of what a program transformation system is really compiler technology. So what a program transformation system has to do is it has to read the source text, it has to analyze it for the places where it needs some attention, has to transform it, and then has to spit it back out again in a form that can be reused by whatever the programmer wanted to do it for. So that parse, analyze, transform, pretty print, that information, that technology, it's in the literature. It's been the compiler literature, and the compiler guys have been developing it over the last 50 years. It's there for the taking. The way I think about what we do in terms of technology is we walk to the back end of the Stanford Computer Science bookstore, which is the compiler wall. Okay, and we take the next book off the shelf. Okay, take it home and look at it and say, what part of this book can we use? Build that piece of machinery into our system. Take that book, set it in the pile, back to the Stanford Computer Science bookstore. Okay, so we do this sort of like, one new interesting thing every year. But it's not AI. It's known how to do. This gets into the funny phrase about it's AI if you don't know how to do it,
Mm,
right? And so when anybody says it's AI, he's condemning himself. I'm using AI. He's condemning himself. I don't know how to do it. I don't know how to tell you what I'm doing, right? All right, so there's AI. So we're not AI, even though this stuff was labeled AI. There have been two AI winters. Okay, that happened already. Okay, there was the expert systems thing, and there was the neural net thing. Okay, in the late '90s, that failed, came roaring back in 2015. Okay, I think a lot of this AI stuff, I'm kind of surprised. Okay, when I play with it, and I haven't played with it a lot, I get sort of remarkably interesting answers, and I'm not really sure what to make of that. It's impressive. It's impressive what they can seem to answer as questions. You formulate some questions, say, explain to me what a qubit is. Okay, you get back something that reads pretty intelligently. The problem, this stuff is all extracted, okay, by scraping the net. Okay, so what these AI engines know is what the net knows. All right, how much of the net stuff is correct? 90%? That's good. So you end up with these funny comments and people say, oh, I got my output, it has a hallucination in it. Okay, if you can recognize a hallucination, it might be useful. If you're not smart enough to recognize which part of that thing is hallucination, you're now about to go do something that's wrong, and you don't know why.
yeah,
All right.
exactly.
So the first point, it's based upon fuzzy knowledge. Okay. Second point is, the machinery which does what it does. I don't understand how that works. I don't understand its limitations. I don't understand its strengths. Okay. That doesn't mean it's wrong. Okay. I don't understand the strengths of a crescent wrench either, but it's useful, right? So you can use it. But the question is, how are you going to use it? The idea of many companies that we're competing against now, okay, is we're using AI in our transformation technology. Half of this, I think, is a sales trick. Salesmen will sell you anything, any way they can. Okay, hi, I have snake oil. It cures everything, right? Like, yeah, I'm sorry. If you don't know, tell me what the limits are. I'm not sure I trust you in terms of what you're offering me. So that's one of the problems. Okay, and the second problem, I guess, is the category of why is it COBOL works? Use COBOL. You like it. Why does it work? And the answer is because it's okay to be wrong. Okay. It only has to be 90% right and it's useful by itself.
Right.
Okay. Let's try the variation of that, okay, with converting application to that system. So imagine I have 10,000 modules that make up an application, and I pick one of them at random. They're all in COBOL. I pick one of them at random and say, I'm going to convert this using AI. And I give it to my favorite AI tool, which just so happens to take in COBOL of that particular dialect, and that's an interesting disease in its own right. Takes in that particular piece of COBOL, it spits out a piece of Java. And let's even assume that it didn't hallucinate anywhere. If it did, I got a broken piece of code. Now I have to debug it. I don't know what it does because by definition, I just picked one at random, right?
Right.
Okay. Well, so let's assume it didn't hallucinate, right? All right. So I've got this Java program and I got 9,999 programs in COBOL. How do I run this system? If the COBOL doesn't know about the Java, okay, the Java might be designed to sort of know something about the COBOL, maybe sort of, kind of, okay? But it's hard to believe I can run one module and then make that work. Well, if
Mm,
you can't do it incrementally like that, how are you going to do it? Do you pick 1,000 modules and convert them all and hope none of them have hallucinations in them? Okay, I don't see how this works. Okay, what apparently is going on is these companies saying, well, we'll use the AI to explain what the code does,
yeah.
and then we'll get a programmer to go code that. I see. So what you're doing is guessing at what the spec for this module is, guessing, okay, and then you're giving this spec, which you guessed, it's written in sort of, in stilted English from the AI, and you're going to give it to a programmer, and he's going to read it, and he's going to try to interpret. If you're lucky, he interprets it right. If you're not lucky, he interprets it wrong. He's going to go build a piece of code that he thinks does that. Okay. Now, does he build it in Java? If he does, you got the same problem you have if you had a fully automated conversion. How does it play with the rest of the system? How does it put together? Well, you don't have to do that. You could say, let's apply this process in parallel. Okay, I'll get 9,000 programmers. I'll give each one of them an AI explanation for it, and they can all recode these things. And when we're all done, we hope we can put that system together and it all works. What do you think the odds are? Not very
Very
good.
slim.
I have yet to see an actual example of somebody said, I converted this system using AI and I was successful. I keep asking people about this. Nobody's ever pointed me to one that works. Elon Musk says he's going to fix the Social Security Administration using AI in 3 months. Okay. I hope he tries. I hope he fails spectacularly. It would be the appropriate downfall for a guy like that, right? So the AI stuff is, it's got a lot of interesting things in it, but it's not strong enough yet, and it doesn't solve all the problems. It has one more really deep flaw. It's an LLM. It predicts the next word. It's a word predictor. It doesn't reason. Okay, it's really hard to write code or build any kind of interesting engineering artifact without reasoning about how the pieces fit together and what they should do. If it doesn't reason, I don't see how it can do anything interesting. All right. Now, the flip side of the coin, you can ask, does our tool reason? And the answer is, well, yeah, it kind of does. All right. It does a lot of very sort of focused reasoning based upon what the compiler technology books say. Here's how to build a data flow graph. Here's how to follow information along the data flow graph. That's reasoning, right? But it turns out that you can also build reasoning on top of these program transformations. I mean, you basically say, let me take a language of logic, Boolean operators, okay, and various kinds of operands. I can define that language to the tool, okay, and then I can say, okay, tool, go reason about those things, in the sense you can actually apply algebraic transformations on the Boolean logic. That's reasoning. We can kind of do that. We don't do that very much because we don't think we need an awful lot of reasoning inside the box. Okay, if we use our reasoning to shape the transformations that we give it, and that's why I think we get away with it.
Interesting. So, do you see LLMs ever playing a part in your development process?
Well, you've asked a hard question. I look at them and I go like, geez, these seem to work better than I think, okay, in the sense they give you something. Okay, it's certainly better than gibberish. Okay, we don't really know how to apply it, and I will say, as a small company, we have two choices. Okay, go make money, that feeds us. Go play with things, that doesn't feed us. Okay, so if you go play with something, you have to say, if I go play with this, I better be sure I'm going to get something really valuable out of it soon, because otherwise it's just a long-term investment. And that's okay. We've done some of those, right? I'm not convinced enough yet. I'm not convinced enough yet. And I find it surprising that there's now this sort of new problem, okay, which shows up if you look at open source software, what happens, somebody builds an open source application, somebody else doesn't like it, and they immediately fork it. Okay, now I got 27 copies of this application, all of which have been pushed in various odd directions. The LLMs are going exactly that way. ChatGPT came out, and now we got 25 of them. Okay, along with, oh gosh, okay, we'd like to help teach you train your own LLM to do this. So what are you telling me? You're telling me the LLM that you have doesn't work well enough for this, and I have to do something else? So the moment you make me train my own LLM, you also make me responsible for its failure,
Yeah,
right?
it's true.
Okay, so how many people have experience training LLMs for software maintenance? Zero. Okay, we could become one of the first ones to do that. We have enough to do. So at the moment, I'm just watching with amazement, trying to figure out what's going to happen next. And events like Elon Musk are going to be the kinds of things that actually make or break this AI technology. Somebody comes out and has a really spectacular failure with it, we'll have another what's called AI winter. Everybody will go like, we heard all that, everybody been on it, it was all a mistake. Do something else.
Yeah. Well, that seems to be his philosophy is you shoot big, and if it
Well, yeah,
succeeds, you look like a
move fast,
genius. If it
move fast,
fails,
he'll
just move
move
on to the
fast
next.
and break things, but there's a parenthetical after the break things part. Break things, parentheses, in such a way you get a useful result, right? Parentheses. Okay, and the question is is he paying attention to the parenthetical part? And the answer is it's not clear. Okay, he's got 526-year-olds busy hacking at the Social Security Administration. How well is that? They don't know. That place has 100 million lines of code. What kind of dent do you think they can make?
In 3 months.
I actually hear that they managed to shut the SSA website down yesterday.
Oh, yeah, I hadn't heard that.
Yep. Apparently they put in some patch they thought was going to improve it, and that patch wasn't tested. Okay. So one problem we haven't discussed so far is, how do you decide that your answer is good? Okay. And we have to convince the buyer that our answer is going to be good. Okay. And then we actually have to build it such that the answer is good. And it turns out this is hard. What every client wants to know is, does my program do what it used to do? If you're just going to preserve it, right? Does my
Right.
program do what it used to do? Well, Mr. Customer, what does it do? The answer is, I don't know. Okay. So the way you get that explicit, you get a more direct, indirect version of that when you ask them, so how do you test things? And they said, well, I send Joe over to a terminal. He types some stuff in. If it looks like we're done. This happens more often than you can imagine. Very few people actually have serious regression tests for their application. Because in order to build a regression test, first of all, you have to decide you're going to do it. That's expensive. Then you have to go pick a module. Then you have to go guess what the module does. You have to go write your regression test to see if it matches. Okay, and when you're all done, you have a test that tells you that your module does what it already does. So the reward's not very big. right?
Right.
Now,
Right.
when you actually do a migration, suddenly that's very interesting. Okay, what does your application do now? Oh, the regression test tells me. Can I run that same regression test on the target, on the generated code? And if it will say yes, then you can say, okay, I have some confidence that the target, the translated code actually does what the original code does. Okay, well, you can think about that. Now you have to say, all right, how do I write my regression test that ran against COBOL in such a way it will run against C#? That's a major problem in and of its own right.
Yeah.
What people mostly do, okay, is they try and do regression testing against the screen interfaces of the application because they can see on a screen, okay, the input output boxes. The user can point to them and say box, 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 box. Okay, you can say run the test, new boxes, a new screen comes up with new boxes, and you say box, 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 box. It all matches. So if you can go into the user interface, you have some chance of capturing these things. If you
Mhm.
don't go into the user interface, then you have to build what amount to like unit tests or mock tests against the actual code. You have to sit down and write that in COBOL or something like that, figure out how to integrate it into your development environment. Nobody does that. So the screen thing sort of works, sort of, except that the legacy technology for the screens is running off a mainframe with a green screen driven by characters and EBCDIC from the mainframe it kicks. And the green screen and the screen that you have over on the C# side is an emulation of that. It's a piece of HTML that does the same thing. Okay. But the way you access the fields in those two is completely different. The green screen thing coming from the mainframe, it's really hard to access because it's pixels on a screen and it's sitting in front of you on a 3270 terminal. So if you want to access it, you have to go back behind the screen, okay, into the operating system, into Kix, which is the thing that generates the screens, and tap into that somehow. And hardly anybody has that technology available.
Yeah.
Okay. So what tends to happen, at least in our world at this point, is the clients end up not writing, they don't have regression tests for the legacy system as it is. So what they do is they write regression tests that'll run on the modern system, but not on the legacy one. And they validate it by looking at what happens on the legacy system and say, okay, does the modern system do the same thing? And they check it out. But now they have to write a whole bunch of regression tests as part of the migration process to convince themselves it works. There used to be a measure of complexity called function points. You may have heard of these.
Mhm.
No. Okay, you heard about Halstead complexity and cyclomatic complexity, counting lines. There's a whole bunch of people that do metrics by measuring properties of your code. Okay, one of these groups of people were people who proposed something called function metrics. And the idea behind function points, the idea behind function points is a function point was enough code to do something interesting. What that means is 10 to 20 lines of code, as a guess. I'm making that number up. You pick it out. How many function points are there in a 10 million line system? Divide by 50. So you sort of can't test everything. You can't do
Right.
it. But that's what the clients want to do. And eventually they write a bunch of tests. And if they all work, then they're sort of okay with moving on to production. Okay, and so that trick is to get them all to work. So now the question is, how do we rig it so that the translated code doesn't fail? That's the interesting one. Okay, and we do that by a sort of peculiar trick. What we actually do is we sit down and we write about 2 or 3,000 little tiny programs. Each little tiny program is a test written, say, in COBOL. And what that little tiny program does, it tests a feature of COBOL. So here's an example. X equals 1, Y equals 2, Z equals X plus Y. If Z not equal 3, fail. That test, that's simple arithmetic, sort of works. So that's a little tiny program. So you write
Mhm.
that little tiny program. You take that little tiny program and you run it through the translator. You should get out a piece of C# code that actually takes 1 plus 2, adds it to 3, and doesn't fail. All right? Do that for each feature of the language that you can invent. That's why we end up with a couple thousand of these things. So we
Mhm.
have a whole bunch of programs of size 3 to 40 lines, okay, that test various features. Testing index files is a lot of fun because you got to set up a file, put stuff in it, read it back, check it all. Okay. So we have a couple thousand of these programs, okay, and we compile and run these programs every day during our project. Go run all the test cases and go run all the feature test cases and make sure they all work. We also test the compositions work. I have a function call. Let's see if I can call the function with 1 plus 2 as the argument list, which does add work in the context of a function call. Okay, now you can't do too many of those because if you got 2,000 features, you got 4 million variations. You can't do that. But if we test enough things, then things work pretty well. So we try and arrange it so that what the transformation rules do is they generate code that's right because we basically tested the hell out of it on the small. Okay, and then the big programs tend to work pretty well. We do have we're engineers. We make mistakes. Okay. And what I tell the clients is, yeah, we're going to build a translator. We're going to get it wrong. It's normal. Don't get excited. Okay. Because we get it wrong, we'll see it. We'll go back and modify the translator and just run it again. Okay. So our problem is nowhere. And furthermore, if that mistake shows up in 1,000 different translator modules, we fix it in one. All 1,000 get fixed.
Right.
Okay, so our leverage in terms of fixing things is much stronger than you get with sort of conventional programming. You fix one bug, that's it. There's another bug still out there. We fix one bug, we can probably hit 500 more. Okay, they're the same kind. So that
Mm.
gives us a pretty reliable process. It takes a while for us to convince the client that that's what's going to happen because he's fundamentally at the end is like, I got to get something that works. Tell me why. We get him over that hump, we're close to landing. That's the big hump. Is this going to work? Question mark.
Yeah. Yeah. Gosh, there's so much complexity to this. It's really quite incredible.
It is interesting that our first couple of systems when we did this were done completely ad hoc. We had our tool. Okay, we had translation problems. Sit down and start writing your transformation rules. Okay, we're getting more organized. We're now very careful to keep track of all the translated modules that we have so that we can, so that when the client installs them and says it doesn't work, we can say, did you install the right stuff? So we have an image. It has to be this. Did you install this? No? Okay, there's something wrong with your side of the wall.
Right.
One of the other things that shows up quite a lot is the clients have a number of other things they want to do. Okay, I want to clean up this interface. I want to make this available. And those can often turn out to be just sort of custom transformations, okay, that deal with certain things. We have one client that wants to take all the direct keyed file access statements in a program, take them out of that program and move them over to a data access layer. Okay, so that their data engineer can manage this stuff more effectively. That turns out to be a set of transformations. The transformation has to say something complicated, like if you see a keyed file access in this file, okay, then figure out where the right place is to put it in the data access layer and replace the code with a function call that does that. So we can add some kinds of things. So I think of these things as architectural shifts. The original application didn't have a data access layer, and you want us to add one.
Mm.
Okay, there's one that shows up over and over again. So we want our system to be converted into microservices. Okay, we never do that. It's never worth the trouble.
Yeah.
Okay, but it's a hot topic in industry. So when somebody first shows up, they have a list of buzzwords like, can you do microservices? Can you do access layers? Okay, can you generate dynamic screens? Can you generate distributed applications? There's a whole bunch of things they want to do, which are architectural shifts. We go, we could do all that. That will make it more expensive. Sure, you want to do it? And then I usually go like, yeah, no. There's another reason not to do a bunch of architectural. You could do maybe one architectural shift and a migration by itself. If you try and do two, you get a lot of interactions.
Mm.
Okay, and I sort of characterize this as getting heart surgery and a facelift in the same operation.
Mm.
Maybe you don't want to do that. It's like,
Yeah.
let's do one major thing at a time. Okay, so we don't end up with some complication. Oh, look, his nose is bleeding, so he ignores heart. No, not good. Not
Yeah. Yeah, and those things are not directly related, so finding the cause and effect is becomes that much more difficult.
whatever it is. The point is, you don't want to do two major things at once, right?
Yeah. Yeah.
It's too much risk.
Yeah,
We do
absolutely.
we do end up working with the clients quite a bit. A project takes about a year to do, year to 18 months. Okay. It's funny, even though we start out with a translator that can do a 90% conversion of what you walk in with a pile of COBOL code. Okay, in a dialect we happen to know. We can talk about dialects in a minute. In dialect we happen to know. Our translator probably do 90% convert that on day one, right? So you got 10% left. So it can't be that much work, right? Yeah, no, it's like another 10 man years of effort on our tuning our stuff to get through that because that has 10%. It's the complicated part. The automated conversion isn't instant. People are disappointed, but well, there it is. But it's reliable. We've never failed a project we've started, and it gives you a pretty good answer. The other techniques that we see, the ones that are done sort of by hand coding, a lot of those projects fail. You go look up really big failures. Hewlett Packard tried to convert the state of California's DMV software. It's written in assembler. They tried to convert that stuff, okay, over to COBOL about 10 years ago. Failed at the $400 million level.
Oof.
Okay. And now that and we've talked to DMV several times since, they go, yes, we desperately want to move, but people have such a bad memory of their experience with HP. And it's been a decade, right? They have such a
Yeah.
bad experience that like, I don't want to go near that because last one failed big time. Lots of people got hurt, right?
Yeah. Right.
So it's getting it done and getting it done reliably, in my opinion, is the really key feature. If you can't get it done reliably, you should be scared to do this.
Yeah. Yeah. Not
So
not
that's one of the
something
things we
you
bring to the table. We can do this.
yeah, it's not something you jump into just willy-nilly. You gotta do your research and planning and definitely need to take your time before you make that
Right.
decision.
And there's some, that year spent doing tuning of the translator, building more of those tests we were talking about for the regression test to make sure on the small piece to make sure that all works. And then there's a part which is always sort of awkward. Okay, the automated migration stuff. It's easy to get it easy if you have the right technology. Easy to get 99%. We're there for most of the stuff, right? It's harder to get to 99.99%. That's pretty good. That's one line out of 10,000. Right? But if you got 10 million lines, that's actually still a fair number of lines. Now we're going to get to 99.999%. There's a question of how far do you push that? There's a point where you can say, okay, I'm 99.99% converted. I've got 150 errors left across the entire system. What should I do? One, go back and tune the translator some more. Two, time to get out your editor and just cross the finish line. Okay. There's always a little bit of dirt, okay, in the migration. Things that just aren't going to go over well, and the cure for those things is just pounding with a hammer. And it's okay. It's okay in the small where you can control the amount of work that's involved in doing that. It's not okay in the large. You don't want to convert 99%, but that's what people tell you. We get 99% conversion. Yeah, good luck doing that last 1% 10 million line scale. Good luck.
Wow. This has been a really incredible deep dive into this topic. I did not expect you to go this deep in the technical weeds, but it's really fascinating to hear. So I appreciate you sharing that.
It's been, I will say, it's been a truly interesting ride on my part. Okay, watching this whole thing go, right? Because it's like, does this technology really work? Yes, it really works. Okay, what does it take to make it work for different languages, right? We're at the stage where we have, I think, about 30 different front ends for different languages. So we're sort of prepared for people to walk in on us and say, I've got this strange language, or I've got this not very top language. There's what is it? There's a top 10 list of programming languages. What's the name of the list? Okay, and we cover probably those top 10, but there's 200 more below that. Okay, and all the guys in the 200 more below, they have motivation to move because they're in a really weird technology and they're not going to. It's even worse than COBOL. Okay, how can I find a COBOL programmer? I get a Java programmer and I put $100 bills in front of him until he says he'll code in COBOL. Okay, how can I find something for like some weird language? Okay, that you find in 299 down in the list of commonly used languages. You're not going to find that guy.
Yeah. So you're finding yourself having to learn some of those languages from scratch, basically?
Yeah, so one of the things about being a computer scientist, okay, is that I'm not specialist. Well, that's weird. I am a specialist. I know everything about nothing, right? Okay, but this little tiny point. Okay, but you have to be kind of a generalist. Okay, I mean, so I see in a month I see 5 different programming languages I've never seen before. Okay, none of them go anywhere, but people say, "I have this. What can you do with it?" And like, how bad do you want to move? Right? You got to get over that conversation first. But yeah, you see all kinds of stuff. You just all kinds of stuff.
That's a fascinating business you're in. So for the listeners, as we close out here, can you tell them a little bit about how people can find you and what services you guys are making available? Do you have availability if someone wanted to try to take on one of these projects?
Sure. Okay. So our company name is Semantic Designs. We're reachable as www.semanticdesigns, one great big giant word.com. Okay. You can probably also reach us by typing in automated conversion of COBOL in the search window on Google. That will probably find us too. We're good at COBOL. We're actually good at Fortran. Okay. People talk to us about assembler on mainframes, lots of other odd languages. We'd be happy to chat with you, tell you what we can do.
Well, thanks again for joining me, and thanks to everyone for tuning in. Be sure to subscribe, leave a review, and as always, keep pitching, keep building, and keep scaling.
Thanks for listening to this episode of Pitch, Build, Scale. Be sure to subscribe on your favorite podcast provider so you never miss an episode, and we'll see you next time.